And our last speaker of today is Pavel Panteleev, and he's going to tell us about expander-lifted product codes.
Hello, everyone. Thank you for a nice introduction. This is a joint work with Gleb Kovachev. So let us start with classical and quantum LDPC codes. So a classical LDPC code is a linear code with sparse parity check matrices. It is usually represented by a sparse graph called Tanner graph. And so since it's a classical code, so we have a classical picture, we have code words, we have the distance, and we need to put as much as possible code words so that the distance would be high. Okay. Classical DPC codes were introduced by Robert Gallagher in the 60s, and nowadays they're used almost everywhere, and you can find them in SSDs, in Wi-Fi, in 5G. And Gallagher, when he introduced it, he already showed that there exist good families of LDPC codes. But the explicit constructions of LDPC codes remained unknown until very well-known work by Sipser and Spielman, and they also showed that you can also efficiently encode and decode such codes. And a prominent, so the Sipser-Spielman code is just a type of what is called Tanner code. So a Tanner code is a code defined on a graph. So we have a graph, and we put bits on edges, and we put our checks on vertices. And if our checks are satisfied, then we have a code word. And actually, the Sipser-Spielman idea was to use Tanner code. And they showed that if you have an expander graph, and if the expansion is good enough, and if the distance of the local code is also good enough, then the resulting code has these amazing properties, and you can, for example, decode in linear time. Okay. Let us discuss quantum LDPC codes. So quantum LDPC codes are really similar, but instead of, so we can view them just as a couple of classical LDPC codes. And, but unfortunately, to define a proper quantum LDPC code, we need to satisfy this well-known condition. Okay, the parameters of these codes are defined in a similar way, so it's just the number of qubits minus the number of checks. And the minimum distance, so instead of one minimum distance, as we will all know, we have two minimum distances, and we choose the minimum of them. Okay, so we can also represent a quantum LDPC code as a kind of Tanner graph, but instead of two parts, we have three parts. Two corresponds to X and Z checks, and the middle one corresponds to qubits. And the very famous example of quantum LDPC codes, and I suppose everyone in this conference know about, it's Kitaev story code. Okay. And so why we are interested in quantum LDPC codes? I assume that also everyone in this audience know why we are interested, because many people think that they can be used in future fault-tolerant quantum computers. And one of the major problems in this area was the problem of whether there exists a good family of quantum LDPC codes. Okay, before I start discussing our construction, let me remind some algebra related with this construction. So we need a notion of chain complexes. It's just a sequence of vector spaces with this property that two consecutive maps gives you a zero. And so we can define the groups of boundaries and the groups of E-cycles. And since we have this property, we can also consider the quotient group. And why we are interested in chain complexes is because chain complexes can be seen as a generalization of both classical and quantum LDPC codes. In particular, chain complex that consists of two terms, it corresponds to classical LDPC code, and the chain complex that consists of three terms, it naturally corresponds to a quantum LDPC code. And in particular, this property that I mentioned when I defined chain complexes is exactly the property that we require for CSS codes. Okay, and so one of the main ideas behind all this new construction is the idea of tensor product. So, and here I present it in the most general way. So if you have two vector spaces, and if we can consider these vector spaces as modules over some ring, so we can define a tensor product over this ring. Okay, but this were all very abstract algebra. Let us start with something much more simple. So let us start with the classical product codes. So a classical product code, it's just a matrix. It's a code that each code words are matrices, and each column of this matrix, it belongs to code A, and each row belongs to code B. And if we choose parity check matrices for our codes, and we can describe them in a more concise form. Okay, but why I mentioned classical product code, why we are speaking about quantum LDPC code? And the reason is because they are naturally connected. And let me describe this connection using hypergraph product codes. So, okay, now we have a classical product code that I defined before with this compact representation. And looking at this compact representation, we can see how we check that a matrix is a code word. So we multiply this matrix from the left by a matrix A. Yes, and when we do this, we apply this parity check matrix to each row. And if all these syndromes are equal to 0, then it means that each row is a code word of the code A. And we do the same by multiplying this matrix from the right by transposed matrix B. Yes, and if we do this, so we multiply each row of this matrix W and check whether the result is 0. Okay, so we obtain our syndromes, so I call it vertical and horizontal syndromes, but you can easily see that these syndromes, they are not, they have a lot of dependencies. And you can see these dependencies from this very simple equation. Yes, you see that if we have a syndromes U and V, then they should satisfy this additional equation, this additional dependency. So, and now, what we are going to do, we are going to consider this system as a chain complex. Yes, so we divide it in 3 parts. And so we can see the chain complex, and one can easily show that this is exactly the tensor product of these very small chain complexes. And you can see that this classical tensor product code, it corresponds to the second homology of this complex. And hypergraph product code, it corresponds to the first homology. And so here, so I give a slightly not very standard definition of a hypergraph product code, but you can, if you substitute, so if you multiply, you can check that this is exactly the standard definition of hypergraph product codes. But why I chose this different form? So let me explain. This is because when we study hypergraph product codes, we are mostly interested in this case, when the second matrix is transposed, yes? And in this case, you can see that we have a very simple and elegant description of hypergraph product codes, which is much easier to study. And it is well known that if we use this construction, if matrices A and B are the same, and if they correspond to a parity check matrix of some good linear code, then we will get codes with minimum distance that grows as square root of n. So this is a classical result by Tillich and Zemmer. Okay. But the topic of my today's presentation is lifted product code. So what are lifted product code? Lifted product code is a very simple idea. So the idea is just to replace this finite field. So in our case, we can think that finite field is just a field of two elements with a ring with a group algebra, which is a larger ring, yes? And each element of this group algebra, we can think that it can be represented by a tuple of L bits, for example. And in this case, so it's exactly the same definition as before, but instead of individual bits, we have L bits. And we also have two analogs of, we have classical, we have analog of a classical product code. We have this tensor product code over ring. Which is defined in the same way as a classical product code. And we also have a natural analog of a hypergraph product code, which is defined exactly by the same formulas. No modifications is required. And what is really interesting is that it works for arbitrary rings. You do not need any assumptions, any additional assumptions. The definition in this form works just for arbitrary rings. And let us consider the special cases of lifted product codes, which were introduced by Kovalov and Pritko 10 years ago. And sometimes they are also called, now they are also called 2BGA codes. And this special case is just when we consider matrices, one-by-one matrices. Yes, in lifted product code, we consider arbitrary matrices, but let us assume that these matrices are one by one. Then this is just individual elements. In this case, we have a very simple code that can be described like this. And if we consider its parity check matrix, then you can immediately recognize this left-right Kelly graph that was used and that was behind all recent constructions of good LDPC codes. So in some sense, maybe we should also call it, I don't know, Kovalov-Pritko graph, because they introduced it 10 years ago, but of course they considered only the abelian case. Okay, let me just give you some examples of such kind of lifted product code. So the first example is just toric code. If we use the product of two cyclic groups, then we can also obtain hard 3D codes. In fact, we can also obtain a lot of similar codes, like the code that was studied by Yoshida. And also, we can obtain generalized quasi-cyclic generalized bicycle codes that we studied in our paper in 2019 in last QEC. And what is also interesting, you also obtain, as a special case of this construction, very recent breakthrough result by IBM team that showed that these codes are very promising for future fault-tolerant computers. Okay, and what is also interesting that this family of codes has what is usually called the X duality. This particular result was obtained in our joint paper with Gleb Kalachov, and it was also reproduced in this recent IBM paper. Okay. But our main topic is not just lifted product code, but expander lifted product code. Okay, what is the main idea? The main idea is quite simple. So instead of just using some very simple codes as matrix A and B, let us use the expander codes. And the particular expander code that we want to use is so-called Zemmer codes. Zemmer codes are some slight modification of Zipser-Spielman code. They are defined not on a Cayley graph, but they are defined on rather on two lift of Cayley graph. And for this particular code, you can represent its parity check matrix in a very simple form. So this is a parity check matrix, and each element of this matrix is an element of the group algebra. So this is a 2M by W matrix, and each element is an element of the group algebra. And so here I assume that H1, HW is a parity check matrix of this that corresponds to H. Okay, and the code that we obtain is shown here. But the main question, how do you get a good family of codes? It is trivial to show that such codes has constant rate under some special conditions, but it is really trivial just by counting the number of X and Z checks. But what about the minimum distance? How do you get minimum distance? So you can try to use some analog. So some analog of hypergraph product construction. Yes, for example, you can use the same matrix. And this is similar to the idea that was conjectured to give good codes by Brookman and Eberhard in their famous conjecture that was also mentioned today. And what is interesting that it looks like this conjecture is false. Okay, so let me explain why I think that it is false. So the problem is that when you apply this construction to the same matrix, you can obtain a very simple counterexample. So this counterexample can be seen from this new formulation of hypergraph product codes and lifted product codes. So if you look at this equation that define this code, you can see that it defines U and V such that HU equal to VH. But if you substitute U and V equal to identity matrices, then you always get a code word. And moreover, it is not just a code word, but it's a non-degenerate code word because you cannot obtain it from the lower part. So sorry, I forget to mention that. So I define the code as so in the upper part I define this the set of OX errors, and in the lower part I define the set of stabilizers. Yes, X stabilizers. Okay, and actually the same counterexample works for arbitrary code of the form when you multiply complex by its dual. Okay, what is the difference between expander lifted product codes and the previous idea? So the main difference is that first of all, we of course use a very similar approach. So this approach was proposed independently in these two papers. So the idea was just to combine Zipser-Spielman code using tensor product of group algebra, and you can phrase it in terms of balance product. You can phrase it in terms of fiber bounds, fiber bundles. You can phrase it in terms of covering of product of graphs. So it really doesn't matter. And actually, the main ingredient, so the first ingredient only gives you, as you saw from the previous example, it only gives you constant rate. It cannot give you linear minimum distance. And the secret ingredient, the second secret ingredient that actually gives it linear minimum distance was inspired by another paper it was a paper that used high-dimensional expanders to construct LDPC codes. And a particular property that we borrowed from this paper is a so-called co-boundary expansion. And we reformulated this co-boundary expansion for product codes, and it turned out that this notion is intimately related with robustly testable codes. And if you have this property, then together you obtain good codes. Okay. So here's just some slide about this co-boundary expansion, so you could understand what it means. So basically, we have this product code, and I represent it as a complex. And we require, you can define this property in a similar way. So you choose, so you have a product code, and you can choose some code words, some rows from some code A, and some columns from some code B. And you want, and when you choose them, yes, you obtain some, you sum this together. As is shown in this chain complex. And so you are interested in this value, so that is shown below. And so unfortunately, I don't have enough time to give a lot of details, but the bottom line is that this property naturally generalizes co-boundary expansion of bipartite graph. So why bipartite graph? Because product codes, it is well known that product codes are Tanner, if we consider them as Tanner codes, they are Tanner codes on bipartite graphs. And if we choose as these codes A and B, if we choose just repetition code, then we obtain exactly the co-boundary expansion of this bipartite graph. So it's a natural generalization of co-boundary expansion. Okay, I think I don't have more time. Yes, maybe. Okay, I will go. Let me also slightly explain what I mean by lifted product and why we call it lifted product. So first of all, let us consider the idea of the lift of the graph. So we have a graph, and to each edge, we assign some permutation. And this permutation is a permutation on some finite set that we call a fiber. And then we obtain L times bigger graph, and we replace each edge by L corpus, and we use exactly this permutation as a perfect matching. And we obtain this large graph. And so here you can see an example of this graph, how we can do this. So here, 0, 2, and 1, these are just elements of the group of 3 elements. And so these are just shifts. And here you can see the resulting graph. And what is interesting that this lifting construction can be used not only with graphs, but also with codes, since they're also defined by graphs. But they also can be used with circuits and some other stuff that can be represented by graphs. Okay, and this idea is very important in designing classical DPC codes, because classical DPC codes are usually designed in 2 stages. First, we design this small graph called base graph, and then we lift it and obtain a large graph. This is exactly, for example, how codes from Wi-Fi 5G are designed. And the idea of the lifted LDPC codes is just to use this idea for quantum codes. Yes, if we know how to lift classical code, maybe we can also know how to lift quantum codes. And the idea is that we can lift hypergraph product codes. So I don't know how to lift arbitrary quantum code, but I know how to lift hypergraph product code. And actually, the idea is very simple. So you hypergraph product codes in terms of graph theory, this is just a Cartesian product of graphs, yes? And what we do, we just lift the Cartesian product of graphs. And the same thing, I should say, can be explained as a balanced product of cell complexes, and it also can be explained as a graph bundles. Okay, let me skip this. And let us finish with a set of open problems. So first of all, of course, the next major open problem is whether QLTC codes exist, good QLTC codes. And the natural candidate is a complex with 5 terms instead of 3. Another problem that I think is also very interesting, so now we know how to decode efficiently, now we know how to decode using single shot, but do we know how to decode from circuit-based model efficiently? Another problem is how to design universal quantum gates for general QLDPC codes, and maybe also very interesting problem, whether we can use some similar ideas to construct self-correcting memory, maybe in 3 dimensions. So thank you for your attention.
Thank you for the talk. When you are constructing when you take the tensor product in your module, what happens if you choose? Is it somewhat canonical? And did you find any other choices of defining that tensor product for the module?
Sorry, could you repeat the last sentence?
Did you find other choices for if you were to change the definition of the tensor product of your module for the product codes construction? What kind of codes do you get?
If I change the definition of tensor product, but to what definition?
Did you try any other definitions that were interesting?
Okay. I think it's an interesting idea because with the current definition, because tensor products over non-commutative rings can be only defined once. Yes, after you define it, you no longer can define tensor product, other tensor products. But I'm not sure that we need tensor products to generalize our definition. I think that much more promising approach is to generalize the idea of the lift, because we lift the product of several graphs, of 2 or maybe several graphs. But there are other cubic complexes that looks like product of graphs. And there is a paper that I found recently that shows that you can lift these complexes and you can obtain Ramanujan graphs in each direction. So I think this is not a tensor product construction. This is a generalization of the lift.
Thank you very much.
Okay.
Thank you for nice talk. Regarding an open problem, you're mentioning a 5 chain. And if I open another paper, some people say so graph action is only from left to right. So this is an inherently seemingly 2-dimensional thing. And would this be a right direction to pursue this, or you think there must be some other direction to achieve this?
For what problem?
To construct 5-term complex to solve QLTC conjecture, if possible. I'm just asking your opinion.
So currently, I should say that we do not know some concrete example, some concrete idea that I personally think that will work. But as I said, so there is a hope that you can generalize you can generalize this idea of the covering. Yes, you can cover, you can construct covering not only of product of graphs. Yes, you can construct covering of other cubic complexes. And in my view, this is a way to go. Another way to go maybe is to consider not only cubic complexes, but also simplicial complexes, because some of the simplicial complexes, they have some symmetry, and you can, for example, apply balanced product construction to them.
Thank you for the answer.
I think we're out of time, so let's thank Pavel and all the speakers from today's session. And just some logistics about dinner. Is it